Students, students, welcome to the second live session of the course, Solar Energy Engineering and Technology. So here in this live session, mostly I will be discussing the module 5 to 8. So in module 5, basically we have discussed about standalone photovoltaic system. In module 6, grid connected PV systems were elaborated. Fundamentals of flat plate collectors were discussed in module 7. And in module 8, liquid flat plate collectors were discussed. As far as the content in lecture 1 and lecture 2 of module 5 is concerned, we have basically covered standalone PV systems, which comprise of components like PV module, charge controller, battery, inverter, load, and then design steps of standalone PV system. Of course, we have solved few practical examples to strengthen the understanding. In lecture 1 of module 6, grid connected PV systems were elaborated, wherein layouts of grid connected PV systems were discussed. Different components of a grid connected PV systems were also categorically studied, and selection of equipments for the grid connected PV systems were considered, and also a role of different components for maximization of PV systems efficiencies has also been studied. The design of grid connected PV systems were discussed in lecture 2 of module 6. So what are the different parameters like voltage, current, power ratings of modules and inverters? How these parameters are to be considered as matching parameters while designing a grid connected PV systems. And also the design steps, sizing of inverters, and then demonstration of a design system has been presented at the end of the lecture 2. In lecture 3 of module 6, performance analysis of the grid connected systems were discussed. And so we have studied systematically the performance analysis of a grid connected PV system. An example was discussed to determine the energy yield, specific yield, performance ratio, capacity utilization factor, and average system efficiency of a grid connected PV system. As you can see here, we have solar modules. Then these modules are connected with inverter, and this is known as DC cable. And then we'll have AC cable when this inverter converts DC current to alternating current. Then we can have utilities. And of course, in this figure, we have shown one meter. Normally, this is known as net meter or smart meters. And then this energy goes to the grid, or we can take the grid, take the energy from the grid whenever required. In lecture 1 of module 7, we have discussed collector fundamentals, which are thermal collectors, starting with classification of collectors, then different components of a collector, then performance analysis of a flat plate collector, then transmissivity estimation based on reflection, refraction, and absorptions were elaborated. And also we have studied what will happen if solar radiation falls at certain angles. And also we have practically understood like what are the significance of transmissivity and absorptivity product. Also, most interestingly, we have done some critical observations on instantaneous efficiency and stagnation temperature. So if we are interested to write, like you have QU is the useful heat gain, and then you have say S is the amount of solar flux received by the observer plate. Okay, and this may be your I, and then transmissivity alpha. Okay, and this will be average minus, or you can say this may be I multiplied by this, and this will be something like S. Okay, and this is the I is the amount of radiation which is falling on the glass cover, and this S is the amount of radiation which is received by the absorber, and then you have QL. Okay, so by knowing this energy balance, we can calculate what is the stagnation temperature. That means when we are not collecting the water, heated water throughout the day, then under that condition, we can achieve the maximum temperature. Okay, so that means QE will be 0, and then this I multiplied by tau into alpha average is equal to QL. So this will be something like this, and this is nothing but S. Okay. So this temperature is very, very important because this is one of the design parameters. Once you know this stagnation temperature, then we can select the appropriate material for the particular application. Then in module 7, lecture 2, we have primarily discussed about different modes of heat transfer like conduction, convection, radiation. Also, we have studied the non-dimensional numbers related to the heat transfer. And also we have solved few number of numericals to estimate the heat transfer coefficient at different conditions. So these fundamentals are very, very important in order to design a solar thermal collector. In lecture 1 of module 8, primarily we have discussed about collector losses and loss estimation. So heat loss from the collector, how heat loss is taking place, and what are the different loss coefficients like top loss, bottom loss, side loss, overall loss coefficients. And then what are different techniques we use to calculate the losses which are associated with flat plate collector. It may be iterative technique or it may be some kind of correlation applications. So as far as collector losses are concerned, we can have this kind of configurations. So if you consider this is a sectional view of flat plate collector, so this is insulation to reduce the heat losses. This is side part and this is the bottom part, and heat loss is taking place from the top as well, right? So if we are interested about energy balance on the observer plate, so it appears something like this. QU is equal to AP multiplied by S minus Q into L. Okay, so as I say, this S is a complex function, but we can simplify sometimes only I into tau into alpha average. Okay, that's how we have written in the earlier slides. So this term is for the amount of energy which is received here in the observer plate, and QL is the losses. So it take care of all the losses like top losses, side losses, and bottom losses, right? And QU is the amount of useful heat gain, right? Normally the tubes are attached below this observer plate, and then we can find out what is the useful heat gain, right? So heat loss from the collector can be calculated by using this mathematical expression. QL is equal to UL multiplied by AP and then multiplied by TPM minus TA. So what is TPM? TPM is the average temperature of the observer plate and TA is the temperature of the surrounding air. Okay, and AP is the area of the observer plate. So this is the area, this part. So you have to go across the screen. So that's how we can calculate the area, and this is the overall loss coefficients. Now, if we are interested to find out this QL, because this QL is sum of QT plus QB plus QS. Okay, so now we will show this QT, QB and QS, how they are related with some loss coefficients. So here you can see the rate at which heat is lost from the top can be represented by using this equation. QT is equal to UT multiplied by AP and then the temperature difference between the main plate and ambient, right? Then accordingly you can do for other heat losses as well, like from bottom and the sides, right? So if we add these three components, QT plus QB plus QS, so it will be something like this, because this temperature difference is common for all the three equations. So that's how we can write QL is sum of QT, QB and QS. Okay. So finally also we can relate like overall loss coefficient, which is represented by UL, is nothing but the sum of top loss coefficient, bottom loss coefficient and side loss coefficient. You must understand why we have calculated this UL. The overall loss coefficient, this is UL, is a measure of all the losses, right? So once we know the losses, then we can take appropriate measure to reduce the losses. And also we must check whether these losses are falling in the range suggested by the designer, right? So normally this value should be in the range of 2 to 10 watt meter square Kelvin, right? So if it is beyond that, then so your design is not correct. Then we need to think of modifying your earlier assumption, okay, or design. So in lecture 2 of module 8, primarily we have discussed energy balance of an observer plate, then thermal resistance network, then temperature profile of a flat plate collector, then analysis of collector efficiency factor, analysis of collector heat removal factor, instantaneous efficiency, series and parallel connections of the collectors. So what condition we need to connect different collectors in series, and what condition we need to connect different collectors in parallel. So we must know all those parameters, then only we can design appropriately. And here just to show about some of the considerations, already we are quite familiar about this energy balance equation. QU is equal to AP multiplied by S minus QL, and also we know how to represent this QL and what is S, which is already known to us. So if we substitute these values, then we can simplify or we can modify our energy balance equation of something like this. Then further we can modify the expression. Why we need to do this? Because sometimes this temperature TPM is very difficult to calculate. So our primary concern is to modify this expression so that we can do the calculation very easily. So if you notice it very critically, then you can see here the change in temperature difference here. So here is the TPM minus TA and here is the TF minus TA. So TF is the fluid temperature, right? So further this can be modified, and this is first done by Hotel-Wheeler-Bliss, and that's why this equation is known as Hotel-Wheeler-Bliss equation. So this is something like FR multiplied by AP in bracket S minus UL, again multiplication of temperature difference between fluid inlet temperature and ambient temperature. So these values are always known. Ambient temperature is known and fluid inlet temperature is known. So that way we don't have to use another methodology to find out these temperatures. So only temperature sensor is sufficient to find out this temperature difference. Only what is remaining is FR. So what is FR? FR is the collector heat removal factor, which is defined as the ratio of actual useful heat collection rate to the useful heat collection rate, which would occur if the collector absorber plate are at the temperature of TFI everywhere, and each value varies from 0 to 1. Higher is the better. And also here in this equation, where QV is represented in terms of TF, this is the mean fluid temperature, and this F this is the collector efficiency factor, and each value varies from 0.8 to 0.95. And you can see this FR, collector heat removal factor, can be calculated by using this expression, where F this value is also required. Fine. So you must know why we have simplified this energy balance equation to this equation to make our calculation easier. In lecture 3 of module 8, we have primarily discussed about different factors which influences the performance of a flat plate collector. So what are different factors we have? Selective surfaces, like we can lay some kind of chemicals or maybe some kind of material over the absorber plate, which increases the absorptivity of the solar radiation and reduces the emissivity of the outgoing radiation. And then number of covers. So what number of cover is appropriate for maximization of energy received in the collector? Spacing, then collector till, then dust on the top cover. And of course, we have studied about evacuated tube collectors, because these collectors are very efficient compared to the flat plate collector, because the losses are reduced by providing evacuation between the tubes. And in lecture 4 of module 8, primarily we have discussed two components: testing of liquid flat plate collector and its application. So this is the configurations by which we can test a liquid flat plate collector. Suppose this flat plate collector need to be tested, then we need to make some kind of arrangement like cooling water with heat exchanger, because when water is coming out from this collector, it's a heated water. So what we need to do, we need to perform the experiments at constant temperature. So we need to cool it and store it. And sometimes if we see the temperature drop is significant, then again we need to heat it so that we can circulate the water at a constant flow rate at constant temperature. Okay, so that's how we can perform the experiments, and minimum 4 days we need to perform the experiments. That means every day 4 sets of experiments, starting from 11 o'clock, then 11:30, then 12:30, and 1 o'clock. So that means 4 into 4, minimum 16 sets of readings are required to characterize a liquid flat plate collector. And as far as applications are concerned, the liquid flat plate collector can be applied in indoor swimming pool, then water heating, then milk pasteurization, power generation, drying, solar water heater for biogas, or maybe slurry drying. So we can have plenty of applications because it will generate thermal energy. So you know what are different applications of thermal energy. So this is all about the content we have covered during this time, like end of the live session 1 to the live session 2. So thank you very much for your attention. So if you have any queries, please go ahead. I'll be happy to answer. If you have any questions. Yeah, Santi. So I think this is quite clearly displayed in the NPTEL SWAM portal. Uh, Please refer to the website. Maybe no, I will respond to it in the discussion forum. I'll just give the information. So when is the last date to register for the exam? Thank you. So if you have any technical questions, you can ask. In 5 minutes, you will leave. Okay, then thank you very much for attending this live session 2 of the course Solar Energy Engineering and Technology. So thank you very much. See you soon. All the best for the exam.